Hello and welcome to the second episode of, episode 1, second video of Rustin Bitcoin. Today on the Rust side, we're going to be talking about structs and how to implement behaviors for a specific or custom data type. And on the crypto Bitcoin side, we're going to talk about modular arithmetic or finite fields, the building blocks for cryptography. Now, let's get started with the content. First of all, we need to talk about finite fields. What is a finite field? It's a set with a finite number of elements. In here, I've pasted this one. This is just an example. It could be different one, but a finite number of elements for which the basic operations that we know, addition, subtraction, multiplication, and division, I say it with quotation marks. Division, we'll see when we get to it, why I say it like that. All are defined. So those four operations are defined for the elements of the field, which are addition, subtraction, multiplication, and division. And the field itself has something that we call the order, which is basically how many elements does it contain. In this case, it is a field with the order 13. And we are going to be interested in the fields that have orders that are either p or p to the k, where p is a prime number. All right. Why are we interested in them? Well, this type of field, these fields specifically have some certain properties that become useful or allow for certain things. Hopefully, as we go through the videos, we'll discover which of these properties I'm talking about right now that allow for the building blocks of cryptography. And yes, how do we work with them? Basically, with what we call modular arithmetic, which you might be familiar with it. It's also known as clock arithmetic or clock math. And basically, a brief, very simple explanation here is we take one element, in the case of an addition, 7, and then we do plus 8. So it's going to be 15, and then we take the modulus of that, of the order of the field, which in this case is 13. It ends up like 2. If you are thinking about it with the clock analogy, basically we're going to go around like this. So we would have 7 and then plus 8, 1, 2, 3, 4, 5, 6, 7, 8, and we end up with 2. That's a very brief explanation or simplified explanation. If you want to learn more about the math concepts, how to derive some of the things that we're going to be using here today, there are going to be some of the resources that I've used on the description of the video. I'm going to post the links. Some of them are Introduction to Cryptography lectures by Christoph Parr. Also, the Khan Academy videos for modular arithmetic are pretty good. And for some other things, Computer File on YouTube. These are all on YouTube, by the way. Have some pretty good videos that I like. Now, I think with that, we can get started into the Rust part of the video. Since we're going to be working with modular arithmetic, let's create a package, a Rust package. We can do this by invoking cargo new, and then let's call it modular arithmetic. Right, so this will create a new folder for us with whatever we need. And there you go, modular arithmetic. We open the file. So now what we want to do, and let me copy or bring this over from this file, is to represent somehow this finite field elements. So first of all, in Rust, we can represent a custom data type or pack together related data by using struct. Let's do this with the struct keyword. Then we need to give it a name. In this case, we're going to call it field element. Open curly braces. And now inside of this, we're going to put the data that we want to group. We do this by giving names to the fields. So first one's going to be num, and we need to specify a type. In this case, we're going to be using U64, which is an unsigned integer that can hold up to 64 bits. And we need another field, which is called prime. Let's do U64 for now. That is going to hold the value or the order of the field to which the element belongs. That's it. Basically, we've defined this, and now if we want to go ahead and use it, we can do that on the main. Let's try it out. So we do what we call binding a variable. In this case, we do let a, which is going to represent an element for us, and we call the struct name that we gave, open curly braces, and now we're going to do, for the num field, we're going to assign the value, in this case 7, and for the prime field, we're going to assign 13. Right, okay. That's it. And we can print it out underneath just to see the two fields. Field element, the formatters, and we can have it like this, right? We're going to be calling the first one, which is going to be a.num. This is how we access the members of the struct, and then a.prime. We can go ahead down here and let's go into the folder first, and we can do cargo run. Everything looks good, right? It printed out to the terminal. But now that we have this element, we need to think about how are we going to implement a behavior for it, or like functions that are associated with it. The way we do this in Rust is by using an implementation block, and this is done like so, right? Impl and then field element. So this is going to let Rust know that whatever we have inside of this block is going to be, well, related or associated with the field element. And we can create a function which is going to look like this. We need the name for the function, and then fn at the beginning, and now the parameters of the function. In this case, we're going to accept the use num, and we specify the type as well in here, and a prime, which is going to be U64 as well. We need to specify as well the return type for the function, or what are we returning. In this case, it's going to be self. And self with a capital S here basically refers to the field element. So it's indicating to us that it's going to return a field element. That's the way it works with the implementation block. Now, the useful thing about having a function is that we can have certain behaviors, and reuse them. So we can go ahead and take advantage of that and check also that whenever we're starting or initializing a new instance of the struct, we need to actually check sorry, something weird is going on with my keyboard. There you go. We can check that num must be in range from 0 to p-1. Right, and once we're gonna make that assertion, we can now return an instance of of the field element struct, which we do again by using self with a capital S. Quick little note here. This is shorthand for something that looks like this, prime and prime. But in Rust, whenever we are doing this and the parameter names are the same as the fields that we are assigning them, basically we can shorthand it. So let's go back to the initial way. There you go. And now we can do one more method or associated function. Display, which it's gonna take self. You can tell this one's different because it doesn't have a capital S. It might be a minor thing, but capital S here is going to refer to an instance, not to the type itself, but to the instance. And let's do for this one, you know, this, since we're going to be reusing that a lot. And self a.num and then self.prime. There you go. Now that we have it, we can go ahead and try it out. Let's do let be another variable binding. Then we do field element, which is our struct, and then we access whatever we have defined under the implementation block, like this. Two colons, two colons, one after the other, new. And we're gonna give it whatever we need. In this case, let's try 8 for the number and 13 again for prime. And underneath it, we can use our new method display to actually check it out. We can go ahead and do cargo run. And we get a compiler error, which is good that we get it down here. The Rust compiler messages are pretty good, at least, yeah, for me, I found them pretty useful. So you can tell, it tells you exactly where we need to add, what we're missing. And we are missing a semicolon here. Basically, it must, the semicolon here is missing, and we can go ahead and run it now. There you go, we can see it work. And you might be wondering why, or maybe you weren't wondering, right? But might be a good time to address it. You can see here that, this one has a semicolon, but this one doesn't have any, and the Rust compiler didn't complain. So in Rust, coming from C, this one I found a little bit weird in the beginning. But basically, it's statements versus expressions, right? It's an expression-based language, meaning that the functions, they need to return an expression. And whenever we're returning an expression, the difference between a statement and an expression is that an expression actually returns a value. And we make this distinction between statements and expressions by having semicolons at the end of it. So this one's a statement, and since this is our return part for the function, we don't need a semicolon right there. That's good to know, I guess, or good to be familiar with, right? Because otherwise you would be wondering why this one has it and why does this one not need it. And once we have that, we can, then extend the functions that we've kind of made here to include the basic operations that we were talking before, which are addition, subtraction, multiplication, and finally division. Let's call it division like this for now. Yeah, before going for the addition function, we can actually create another one, which is going to be equals, and we're going to be taking self, and then we're going to be taking another parameter, other, and we're going to take a reference to self as well. At this function, we wanted to return a Boolean value, and what we want to do here is just basically check if two of these elements are equal. And it's not a simple like comparison like with integers, because we have two things that we need to compare. Number one, the first one is the number itself, and then the second one is the order or prime, the order of the field. So let's go ahead and do it. So it's going to be for self num equals other dot num and self dot prime equals other dot prime. And this is basically gonna return a boolean, so we need to specify that on the function. Okay, and we can go ahead and do the addition. So let's actually copy from here and change what we need. Let's call it addition. And it's gonna take the same thing, one instance, and then the other field element. This one's not gonna return a boolean, it's gonna return a field element. And let's check before we proceed another assertion. So let's use this line here. So whenever we're gonna perform these operations, we do need to make sure that self prime, that they are on the same field. So other prime there you go. And then we can return an instance of the field element struct. Let's initialize it like this. Sorry, we're gonna do self. We could do actually this new. And inside of this, we're gonna need two things. The first one is the number, and the second one is the prime. Let's return the prime from the start. There you go. And now for the first thing, for the first parameter that we're gonna pass, let's take an example here quickly. So let's say we're gonna do 7 plus 8. This should be mod 13, and basically 7 plus 8 is 15, then mod 13, it's gonna end up being 2, right? So what we do is we take from self the first number, and then from the other element we take the number as well. And for the mod part, this is something that I learned while studying this, that there's a difference, or in programming languages there's a difference between, actually in math as well, but specifically for Rust, if you go ahead and use what you think is a modulus operator, it is actually the remainder operator. So it will depend on the signs of the dividend, if I'm not mistaken, and it could give us a negative number, but we want to actually have a positive number, so we can use what is called a remainder, the Euclidean remainder. So I think this is the function, and we need to specify in here what we're going to use as to take the modulus. So it's going to be self prime as well. Could be other prime. Let's just do self prime for consistency. And there you go. We have two things, the number and then the order of the field, or prime. We should actually go ahead and try it. So we can have a new variable c, and we can do a dot addition plus take b, and then we can display c. There you go. Method equals is never used. This is just a warning. We're not using it right now, but we can see that the result is actually, yeah, 2. If you don't believe me, I guess you can go ahead and take out your calculator, and we can do that here. 7 plus 8, 15, and then take the mod 13, 2. So far so good. We have addition. Now we can go ahead and do the subtraction as well. We rename the function. We are gonna make the same assertion. They should be on the same field. So we compare the order of the elements, the order of the field. In this case, the prime. And now, before returning the element, there's one extra consideration that we need to take for subtraction. Since we previously said that we are working with unsigned data types, we cannot, or I mean should take care of the case when the first element is smaller than the second element, the element that we're subtracting. So what I want to say is, in this case, 7 minus 8 basically would result in a -1. And since we are having or using unsigned data types, we cannot hold this value. So what we can do, and if you saw some of the videos or you're familiar with modular arithmetic, basically we can shift or go around the clock by adding the modulus, and then we can make sure that it doesn't go below or negative, below 0 or have negative values. We can do that here. Let's do if self dot num, yeah, is less than other than dot num. What we're gonna do is return this. We're gonna return self.num, and we're gonna add to it self.prime before we do the subtraction. Right, so this will guarantee we don't have negative numbers or values. And then we do the subtraction, and then we again take the modulus, or yeah, the modulus, and we can return that now. And for the else part, we can go ahead and just, return it as we had it. So without this extra addition, we can just do the subtraction directly. I propose we go ahead and test this. So A, let's try the first one, subtraction, B, and then once again, D display. Cargo run. We have the same warning, actually, that is fine. And then we have 12 and 13. So should be, yeah, you shouldn't believe me completely. And let's go ahead and do it. So let's do 7. Actually, yeah, sorry. Yeah, 7 minus 8. Minus 1, and then we do mod 13. Basically, we're gonna shift it 12 to the right. And yes, we get 12. 13, not 12 to the right. 13, we're gonna shift it 13, and then we get 12. Same as here. So far, we have addition, subtraction, and it's working. Now for multiplication, what we can do, since it's gonna be straightforward, this one's gonna be straightforward. Let's go ahead and copy the addition function. And we can rename this one to mult. And now looking at the other names, it'd be better, to make them shorter, just for convenience, and add as well. Yeah, so multiplication is going to take as well another instance of a field element. The number we're going to multiply by, or field element as well, which is self, we're going to make the same assertion, but in this section here, we're going to do the multiplication instead of the addition. This one should be ready. There you go. We should actually change this one's to the new name, sub. And now let's talk about division. Now for division, you can see I put division in quotation marks, and this is because in the case of division, it does not work as a regular division that we're used to. The difference being that whenever we do A divided by B, we do not end up with fractions or a decimal part. We end up having another element of the finite field, and that is one of the interesting properties about them. So basically we would have a C value. Now we can express this A divided by B by like something like this. So A, due to exponent rules, in this case A times B, where B is raised to the power of -1. And now this -1 is basically what is known as a modular multiplicative inverse, meaning it is a number that when we multiply the original element B times B -1, it ends up being or giving us a 1, being congruent to 1 if you're more into the math vocabulary side of things. So we should end up getting 1. And from this we can see a couple of things. If we are to perform this, we're basically going to need to perform exponentiation or have a function to raise something to a power. So for division, it's not going to be as straightforward as the other cases. We are going to have something like this. Actually, let me copy it from here and we can rename it. So our B would end up being this other.num. And before we can continue with that, we also need a function that performs exponentiation. We can lay out the signature. Basically, we're going to take field element, an exponent. Let's do it. We can see it's a signed value, so let's do integers. We're going to return as well a field element when everything is done at the end. And let's set it up there. Exponentiation. There you go. We have the function. Now we can notice that yes, we can notice that we are using one signed value, and all of our other functions we have kind of avoided that. So let's go ahead and do this little math trick, not call it math trick, but basically by using Fermat's little theorem, one of its forms, we can actually shift the negative exponent, if there is one, into a range that is actually from 0 to p minus 2, p where p is prime, the order of the field. So what I'm talking about here is basically we know from Fermat's little theorem that a to the power of p minus 1, it is equal, or in modular arithmetic is known as a b, it is congruent with 1 mod p. So essentially what this means for, or how the development of this works, is we can multiply by 1, which is essentially multiplying by this, and our negative exponent, if we had one, something like this. So if we had a minus a to the minus 3, we can then multiply everything by a, and it'll end up being out of the negative range. And since the properties of the finite fields, it makes it cyclical, so we can do that and still have an appropriate value. So let's go ahead and we can do that. Let's see if I was properly recording. So yes, we can let n be our exponent, and then we're gonna take the modulus from self dot prime minus 1, and this is gonna be as integer 32, because this is actually unsigned, but not right now. We're casting it. Today we are not gonna see the details of casting in Rust, but maybe in a later video we can see it. And finally, after that is done, we can cast it back to use unsigned 64, which is what we're using. And now that we have that n, we can actually go ahead and return our new field element, which would be new. No, we had already new, which would be self.num to the power of n, and then over here we return self.prime. Gonna write a comment for this. Again. If you want to know more about why we can do this, check out the resources that I'm gonna link in the video description. But yes, so we have that, and we're gonna be raising this to power of n. And let's go ahead and try it. But yes, looking at the message that we have here, basically it's expecting for pow n is expecting U32, and I just realized I cast it here as U64, so we can go ahead and do that, because before it was as well I32. And this time we can check if it compiles. So let's go ahead and do that. Cargo, we can do build actually. Finished. So now it's compiling, and now we have an exponent. We can raise it to the power of -1, and we can go ahead and try to use it here. Basically, let's do inverse, which is going to be the inverse of other.num raised to -1, to the -1. So this is going to be the modular inverse, and once we have that, we can actually multiply it inverse.num, and this is essentially this part, a times b raised to the power of -1. So let's go ahead and actually test that out. We have let d, and finally let's replace this one, a div. Oh, one more thing, we should be taking a reference. We'll talk about this in some later videos, but for now let's keep it like this. And this one should be fine. We can do this as well, I believe. And let d divided by b and we can go ahead and do the display and then run cargo run this time. Method not found in U64. Okay, so what we want to do is actually make sure that it's calling I believe it's not calling from this scope, like from the field element scope. No, what it's actually saying, I wanted to say it wasn't calling the x function, but what it's saying is that for this exponential function is not defined for U64, and I realize now that here I'm calling it unnum, which is a U64 type. So basically it should take the whole field element since we declared here as a parameter self. So we should go ahead and do run. And one more thing, consider borrowing here. This was a mistake actually. We don't need that. And num must be in range from 0 to P1. So basically panicked here. Where can we get this num must be in range from 0 to P-1? Could be from here. And when we call the new constructor, yes. So basically it's giving us a number outside of our field order. And okay, I see why. We should also do the modulus of this. Take the modulus. So it is self.prime. Now I believe this time if we run it should be okay, and yes it is. We get a 9. We get a 9 here, and I had prepared here an online calculator for modular arithmetic. It already has modulus 13 in it, and I believe the numbers we were working with are 7 divided by 8. We see it's 9, and let's see the result that we got. It's 9 as well, so far it's looking like it's good. We'll probably later on set up some tests so that we can actually verify. And a couple other things are that the way we're doing exponentiation right now is probably not the best way to keep doing it. Since the numbers are small now, it should be fine. But as numbers get larger, and they do get larger for cryptography, same thing with the type unsigned 64, we're going to need to do something different. So we're going to need some optimizations and some changes to this basic library for modular arithmetic that we've built. And yeah, that's it. We'll leave that for another video. I think we've reached the end of this one. Hope you enjoyed it, and until the next one.